So in this screencast, we're going to look at the effectiveness of buffer systems and talk about what happens if you add a strong acid or a strong base to a buffered solution. And then we're going to compare those results to what would happen is if you added a strong acid or a strong base to pure water. Now, we learned about the Henderson-Hasselbalch equation and about buffer solutions in our last lesson. So we're going to pick up from how to use the Henderson-Hasselbalch equation to find your pH of the buffer system. And we're going to talk about how to proceed with your calculations if you add a strong acid or strong base to the buffer solution. The first thing you have to do to carry out these calculations is you have to assume that the reaction of the strong acid or the strong base with the buffer system is going to go 100% to completion. And you're going to carry out what we call the stoichiometry calculations. Now, the equation that you use for the stoichiometry part of the calculation is dependent upon if you add a strong base to the buffer system or if you're adding a strong acid. So if you're adding a strong base, remember strong bases dissociate 100%. And so the concentration of the hydroxide ion from that strong base is going to be equal to the original concentration of the strong base. So you're going to take the hydroxide ion from the strong base, and you're going to understand that it's going to get attacked by the buffer system by its opposite. So what I mean by that is if we look at this beaker, consider this to be a buffer system, and I'm just going to use generic formulas here. So let's say this buffer system has a weak acid. Remember, weak acids and their common salt, or a weak base and its common salt. So I'm going to use HA for my weak acid. And so the common ion that would come from the salt would be A- in this case. And likewise, if this were like ammonia, a weak base, you could put like NH3 and then its conjugate acid would be NH4+. But in each buffer system, you have a conjugate acid-base pair. So I'm going to go along with this first picture to explain how to think about these. So this is your buffer system sitting here, and they work as a team. The acid and its conjugate base are kind of tag teaming. And so the objective is to resist a change in pH. It keeps the system's pH buffered at a specific desired pH. So if you're adding a strong base, you're going to take the hydroxide ion concentration, and that hydroxide ion is going to get attacked by its opposite. So since this is a base in the buffer system, the acid is going to attack it. And the goal of the acid is to snuff it out. It wants to get rid of all of it and consume all of the hydroxide ion that's added. That is the goal. So the acid in the buffering pair will attack a base. So that's why here I have OH plus HA. And so now think about what happens. If HA is an acid, it's going to donate a hydrogen ion to the hydroxide. That's going to form water, and it will leave behind A-. So this will be the reaction that you will use for the stoichiometry if you're adding a strong base to a buffer system. It will get attacked by the acid in the buffer system, and then you think through this part. Now, if you were adding a strong acid to the buffer system, so let me come over here and we'll say instead of adding a base, let's say that you're adding an acid to the buffer system. So if it's a strong acid, acids donate hydrogen ions, and the strong acid would produce 100% hydrogen ions in solution. So as you add the hydrogen ions to the buffer system, the hydrogen ion would get attacked by the buffering component that is its opposite. In this case, it would get attacked by the base, A minus. So the A minus will jump in and snuff all of the hydrogen ions out and consume them completely. So to get your equation for that, the reaction to use, H plus gets attacked by A minus, and it's going to yield HA as the product. Because acids or protonic donors is going to donate itself to the A minus. So this would be your reaction you see here. Now, another way you could represent this, I'm not going to do it this way, but you could represent it as H3O plus A minus would form H. Okay, let's forget that. That is not correct. Okay, I was trying to kind of include the hydronium, but you don't want to use that in this case here. All right, so this is the reaction that you're going to use. Okay? Now, once you've done this, you're going to let it react completely. And I'll show you what I mean by that on the examples in a few minutes. But after that, the second part of this is you're going to carry out the equilibrium calculations. You could either ice your problem, which would be a little bit longer problem. This is the method I do not prefer. Or you can use my preferred method, which is using the Henderson-Hasselbalch equation. Now, remember, the Henderson-Hasselbalch equation is very useful with all buffered systems. When you know the HA and the A minus concentration, you can always use the Henderson-Hasselbalch equation. So let's look at example 3 in your notes. Now, the last example that we did, example 2 in class, the buffer system contained 0.25 molar ammonia and 0.40 molar ammonium chloride. So that was the very last example that we did in class in our last time we met. So we're going to pick up with that. So again, you have ammonia, NH3, and ammonium chloride, and from that the common ion is the ammonium ion. So we're told that we have 0.25 molar of the ammonia, and from the common ion, we're told we have 0.40 molar of the ammonium ion in this buffer system. So here we're starting the next part. So it says calculate the resulting pH of a solution in number 2 after 0.20 molar of sodium hydroxide is added to the buffer system. Now, this particular problem is not in your note pack, but if you would, please add it as the bonus example. All right? So, what we're adding here is sodium hydroxide. So what you want to do is think about, what is sodium hydroxide? Well, it is a strong base. So what do we know about strong bases? We know that they're going to dissociate 100%. So what you want to do is you want to do the stoichiometry first. So you're going to take the OH from the strong base, if it's a strong base that's getting added. And what's going to happen is when you put the OH in this buffer system, think about what's going to attack it. What is going to consume it? Well, since OH is a base, it's going to get consumed by the acid, which is the ammonium ion. So the ammonium ion is what you're going to write down here, NH4 plus. And this is going to be, you're going to assume for the stoichiometry that it's going to 100% react. And I'll explain what that means in just a second with the icing of the problem. Now think about what happens here. Ammonium is going to donate a proton to hydroxide. So when ammonium donates a proton to the hydroxide, hydroxide will become H2O, liquid, and it's going to leave behind the ammonia. Now see, NH3 is showing up over here as a product, and it's also in our buffer system. So keep that in mind and look at the things that are related to each other. So we're going to ice the problem, and we're going to fill in our information that we know. So we're told that 0.20 molar of sodium hydroxide is added. So here we're going to say 0.20 molar. The ammonium concentration is 0.40, so fill that in. And the ammonia is 0.25 molar. So when we say it reacts 100%, this is what I mean. Here's where it is. Your change, instead of defining your change in terms of X, whatever number is your smallest amount, in this case it's hydroxide, it is going to get completely consumed, which means all of this is going to be used up. So you're going to say minus 0.20. Since the ammonium is a reactant, it's going to have to sacrifice some of itself in order to use up the hydroxide. So minus 0.20. And over here, since this is a product, plus 0.20. Now let's do the math. This leaves you with none of the hydroxide, because that's the whole goal of this, is the ammonium ion is going to completely consume hydroxide. And in that process, 0.40 minus 0.20 is going to leave me with 0.20 molar of the ammonium ion. And now here we're adding 0.25 plus 0.20, and that's going to give me 0.45 molar here. So look at what we have at the point that this reaches equilibrium. We have some of the ammonium ion remaining, and we have a concentration of the ammonia. This, remember, is the conjugate acid-base pair, and anytime you know the concentrations of an acid or a base and its conjugate, then you can use Henderson-Hasselbalch. So we're going to use the Henderson-Hasselbalch equation next. Remember, the Henderson-Hasselbalch is pH equals the pKa plus the log of the base over the acid. So in this case, the base is ammonia, NH3, and I always write the formula so I don't mix them up. The acid in this buffering system is NH4 plus. So let's plug in our values. We were told the Kb in example 2, and remember we found the Ka of that when we did example 2 in class. We found the Ka was 5.6 times 10 to the negative 10. So we're going to take the negative log of that, and that gives me the pKa, and the pKa of that is 9.26. So I'm going to go ahead and substitute that in here, 9.26 plus the log. The ammonia concentration is 0.45. The ammonium ion concentration is 0.20. So now we're going to have that the pH is equal to 9.26 plus the log of 0.45 over 0.20. And that gave me 9.61. Now you plug it in to make sure you agree with me on that one. So 9.61 is the pH of the buffer system now. Now what I want to do next is I want to figure out the change in pH. This is just something I'm adding on to compare. So let's see what's the change, the delta pH. So before adding any of this base to this system, we determined in example 2 that the pH for example 2 was, let me go back to my notes on that. .05. So we determined in example 2 the pH was 9.05. So the pH was 9.05, we just figured out it's 9.61. So to get the change in pH, you're going to say 9.61 minus 9.05. So we get a delta or a change in our pH here of this system of 0.56. That's a pretty effective buffer system. All right, let's look at another example. This example is actually on your notes. I think it's actually, these are a little bit out of order, but this was the example number 3 in your note pack. But this also wants us to find the resulting pH of a solution in number 2 after 0.1 molar of HCl is added. Now notice this is a strong acid. So same as before, let's look at what we determined in the last example, example 2. In example 2, we knew we had the ammonia and the ammonium buffering system. We also knew the Ka of this was 5.6 times 10 to the negative 10. So we know that the pKa of that was 9.05. We know from the last example that the ammonia concentration in the buffer system was 0.25 and the ammonium ion concentration was 0.40. And so now we're ready to proceed with the problem. So they say, okay, now you're going to add a strong acid. And from the strong acid, it's the hydrogen ion that's going to affect the pH. So since this is a strong acid, we're adding 0.10 molar of the strong acid. Think about what's going to attack the acid. The only thing that can attack the acid is the opposite of an acid, or the base. So in this case, the ammonia is going to jump in and take charge. The ammonia is going to attack the hydrogen ion. So for the stoichiometry, you're going to take the hydrogen ion from the strong acid, and it's going to get consumed by the base in the buffer system, which is NH3. And this again will be a 100% reaction that takes place. The stoichiometry part will be. So it's ammonia as a base, it's a proton acceptor. So if he takes the proton, it's going to become the ammonium ion. So notice again, by thinking it through, you can figure out what goes where in your reaction. We were told the hydrogen ion concentration that was added was 0.10 molar. Ammonia was 0.25 molar, and ammonium was 0.40 molar. So this is going to react completely, which means all of the hydrogen ion will be consumed, so there's none of it left. In the process, ammonia is going to give a little bit of itself up. It's going to give up 0.10 molar of itself because it's minus 0.10, minus 0.10, and on this side plus 0.10. So the ammonia concentration is going to be 0.15 molar. And the ammonium concentration is going to be 0.50 molar. So Henderson-Hasselbalch equation, I'll put HH. We know pH equals the pKa plus the log of the base NH3 over the acid NH4 plus. So pH equals, remember the pKa is 9.05 plus the log. So at this point, ammonia is 0.15 molar. Ammonium is 0.50 molar. So 9.05 plus the log of 0.15 over 0.50. We'll come over here. That's going to give me the pH is equal to 8.73. So now let's look at our change in pH again. Now remember, the original buffer pH, we determined in number 2 was 9.05. When the acid was added, and you would expect the pH to go down some because you're adding an acid, the pH changed to 8.73. So minus 8.73. And again, we're looking for the change in the pH. So the change in the pH, 9.05 minus 8.73 is 0.32. Now, So the pH does change some, but remember, the point of a buffer system is to resist a large change in pH upon the addition of a strong acid or a strong base. And that's what our blood does to us. Our blood is a very efficient buffering system.